A wind turbine consists of several key components working together to convert wind energy into electricity. Let's explore each of these components and understand their functions. The blades are aerodynamic structures designed to capture wind energy and convert it to rotational motion. Most modern turbines use three blades made of lightweight composite materials like fiberglass reinforced polyester or epoxy. The rotor hub connects the blades to the main shaft. It's a robust component that allows for blade pitch adjustment and transfers the rotational force from the blades to the drivetrain. The nacelle houses critical components including the gearbox, generator, brake systems, cooling mechanisms, and control electronics. It acts as a protective shell for these sensitive components. The tower provides height to access stronger, more consistent winds. Modern utility-scale turbine towers typically range from 80 to 120 meters tall and are constructed from tubular steel or concrete. The foundation is a massive underground structure that anchors the entire turbine. Typically made of reinforced concrete, it's designed to withstand extreme weather conditions and keep the turbine stable for decades. The controller system is the brain of the wind turbine. It monitors and regulates operation, adjusts blade pitch and yaw position based on wind conditions, and implements safety protocols when necessary. The yaw mechanism rotates the nacelle to face the wind direction. It uses motors and gear systems to position the turbine for optimal energy capture, constantly adjusting to changing wind patterns. Various sensors are distributed throughout the turbine to monitor performance and environmental conditions. They track wind speed, direction, temperature, detect vibrations, and mechanical stress, enabling predictive maintenance and optimal operation. All these components work together in a sophisticated system to efficiently convert wind energy into electrical power. Each component plays a crucial role in the efficient operation of the complete wind turbine system, from capturing the wind's energy to delivering clean electricity to the grid. Understanding these components helps us appreciate the engineering behind these towering structures. Wind turbine blades have a carefully designed aerodynamic shape to maximize energy capture. They use the same airfoil principles as airplane wings, with one side curved and the other relatively flat. As wind passes over the blade, it creates a pressure difference: lower pressure on the curved side and higher pressure on the flat side. This pressure differential generates lift force perpendicular to the wind direction. This lift force is what causes the blades to rotate, converting wind energy into mechanical motion. Modern wind turbine blades are typically made from advanced composite materials. These include fiberglass and carbon fiber composites, which provide the necessary strength while keeping the blades lightweight. These properties are crucial as modern turbine blades can reach lengths of 40 to 80 meters, requiring exceptional strength-to-weight ratios. The gearbox is a critical component in most wind turbine designs. In a wind turbine, the gearbox sits between the rotor blades and the electrical generator. The gearbox connects the low-speed shaft, which is attached to the rotor, to the high-speed shaft connected to the generator. Wind turbine blades rotate relatively slowly, typically at about 15 to 20 rotations per minute. However, generators require much higher speeds, between 1,000 and 1,800 RPM, to produce electricity efficiently. The gearbox increases the rotational speed by a factor of 90 to 100 times, enabling efficient electricity generation. Some newer turbine designs use direct drive systems that eliminate the gearbox entirely. In traditional designs, the gearbox connects the rotor to a smaller generator, increasing rotational speed. Direct drive systems connect the rotor directly to a specialized, larger generator that can operate efficiently at lower speeds. Traditional gearbox systems use standard designs with smaller generators, but require more maintenance due to more moving parts. Direct drive turbines eliminate the gearbox, reducing maintenance needs and failure points, but require larger, more specialized generators. In summary, the gearbox is an essential component that enables efficient electricity generation in most wind turbines, though newer designs are exploring alternatives. Wind turbines have a complex relationship between wind speed and how much power they generate. Let's look at the relationship between wind speed and power output using a power curve. Wind turbines start generating electricity at a cut-in speed, typically between 7 and 10 miles per hour. As wind speed increases, power output grows rapidly. The turbine reaches its maximum or rated power at around 25 to 35 miles per hour. Between the rated speed and the cutout speed, the turbine maintains its maximum power output. For safety, the turbine shuts down at the cutout speed, typically around 55 miles per hour, to prevent damage from excessive wind. One of the most important principles in wind energy is the cubic power law. This means that the power available in the wind increases with the cube of the wind speed. When wind speed doubles, the power output increases 8 times. This is why location and height are so critical for wind turbines. Wind turbines are strategically placed in consistently windy locations and at greater heights to maximize power generation. Wind speed increases with height due to less friction from the Earth's surface. This is why modern turbines are built taller. Even a small increase in average wind speed can significantly boost energy production over the lifetime of a wind farm. To summarize, wind turbines operate within specific wind speed ranges and follow the cubic power law, making location and height critical factors for optimal energy production. Wind turbines produce highly variable power output that fluctuates throughout the day based on changing wind conditions. To integrate fluctuating wind power into the electrical grid, sophisticated systems are needed. Grid operators must balance multiple energy sources in real time. Advanced weather forecasting systems predict wind production hours and even days ahead, helping grid operators prepare for changes. When wind power increases or decreases, grid operators adjust other power sources to maintain a stable electricity supply. Energy storage systems are increasingly paired with wind farms to capture excess energy during high winds for use during calm periods. Battery storage systems can rapidly respond to grid demands, storing electricity directly and releasing it when needed within milliseconds. Pumped hydro storage uses excess electricity to pump water to a higher elevation, then releases it through turbines to generate power when needed. Hydrogen production uses electricity to split water into hydrogen and oxygen. The hydrogen can be stored and later used in fuel cells or combined with carbon dioxide to create synthetic fuels. These storage technologies help stabilize the grid, reduce wasted energy during high production, and enable higher levels of renewable energy integration. Smart grid technologies help integrate variable wind power by enabling real-time monitoring, control, and optimization of electricity generation and consumption. Wind farms continuously transmit production data to control centers, which analyze weather forecasts and grid conditions to optimize power flow. The control center sends signals to storage systems, smart homes, and industrial facilities to adjust power consumption based on wind availability. Key features of smart grids include real-time monitoring and forecasting, automated demand response, and dynamic load balancing to match supply with demand. Together, these grid integration and energy storage technologies are making it possible to build reliable electricity systems with increasing amounts of variable wind power.